What is SQL? SQL stands for Structured Query Language. It's a standard programming language specifically designed for managing and manipulating relational databases. SQL allows you to interact with databases to perform tasks such as querying data, updating data, creating and modifying database structures. This SQL statement is used to query or retrieve all records from the employees table. The select to part tells the database to get all columns from the specified table. From employees specifies the table from which the data should be retrieved. This code is a simple example of SQL's ability to interact with databases to fetch data. Why learn SQL? Structured Query Language, SQL, is the standard language for dealing with relational databases. It is used to insert, search, update, delete database records. Knowing SQL allows you to understand and manage the data effectively, which is a crucial skill in many jobs today. This SQL command selects the name column from the employees table where the department column is equal to sales. It exemplifies how SQL can be used to query data from a database based on certain conditions, showcasing why learning SQL is beneficial for managing and analyzing data in various fields such as business, IT, finance, and more. SQL Databases Overview. SQL Structured Query Language is the standard language for managing and manipulating databases. A SQL database is a collection of tables that store data in a structured format, making it easy to access and manage. Each table is made up of rows and columns, where each column has a unique name and a specified data type, and each row represents a unique record. Basic operations on a database include creating tables, inserting data, querying data, updating data, and deleting data. This sequence of SQL commands illustrates basic operations on a SQL database. Create table creates a new table named Students, defining columns for ID, name, and grade. Insert into adds a new record to the table. The select statement retrieves all records from the table. Update modifies existing records, in this case, changing the grade of the student with ID 1. Finally, delete from removes records from the table, here removing the record with ID 1. These operations are fundamental for managing data within SQL databases. SQL Syntax Overview. SQL, Structured Query Language, is used to communicate with a database. Its syntax is designed to allow us to perform tasks such as retrieving data, inserting new data, updating existing data, and deleting data from a database. A basic understanding of SQL syntax involves knowing how to construct queries to interact with a database. Here, we'll focus on a simple select statement to retrieve data. This code snippet is a basic example of a select statement, which is used to retrieve data from a database. Select indicates that data is being selected or retrieved. Column 1, column 2 specifies which columns you want to retrieve from the database. If you want to retrieve all columns, you could replace column 1, column 2 with stow. From table name tells SQL from which table to fetch the data. This basic structure is fundamental for beginning to interact with any relational database. Using SQL IDEs, Integrated Development Environments. SQL Integrated Development Environments, IDEs, are software applications that provide comprehensive facilities to computer programmers and database administrators for software development and database management. These include source code editors, tools to automate database schema creation, and graphical interfaces for query execution. Common SQL IDEs include Microsoft SQL Server Management Studio, SSMS, PostgreSQL's pgadmin, MySQL Workbench, and Oracle SQL Developer. The code snippet select tar from employees is a basic SQL query that can be executed in any SQL IDE. This query retrieves all columns from the table named employees. When executed in a SQL IDE, the IDE's graphical interface would display the query's results in a tabular form, allowing the user to easily view and analyze the data. SQL IDEs also typically provide syntax highlighting, error detection, and query formatting tools to enhance the user experience. Database and table creation. When starting with SQL, the first steps involve creating a database to store your data, and then creating tables within that database to organize the data. A database is like a container for your data, and tables are like compartments within the container, helping you to organize the data in a structured way. The Create Database School statement creates a new database named School. Once the database is created, you use the Use School statement to select it as the active database. After selecting the database, the create table students statement is used to create a new table named students within the school database. This table is defined to have 4 columns: ID, an integer that serves as the primary key; name, a variable character field up to 100 characters; age, an integer; and grade level, an integer. The primary key, ID, uniquely identifies each record in the table. Data types and schema design. In SQL, every column in a table is defined to hold a specific type of data, such as integers, decimal numbers, text, or dates. This choice is critical in defining the table's schema and ensuring data integrity. Let's create a simple table schema for a users table, which includes user ID, username, and sign-up date. In this code, we define a users table with 3 columns. The user ID column is an integer and designated as the primary key, ensuring each value in this column is unique and not null. The username column stores variable character strings, up to a maximum of 50 characters, ideal for usernames. Lastly, the sign-up date column is of the date type, meant for storing dates. This schema design carefully chooses data types that match the kind of data each column will hold, optimizing data storage, integrity, and retrieval. Insert into statement, adding records. The insert into statement in SQL is used to add new rows of data to a table. You specify the table into which the data should be inserted, and then provide the values for each column in the new row. This command is essential for populating tables with data, allowing you to store information in your database. In this code, table name should be replaced with the name of the table you're inserting data into. Column 1, column 2, and column 3 are the names of the columns in the table that you're adding data to. These columns must exist in the table schema. Value 1, value 2, and value 3 are the respective values for these columns in the new row being added. If the table has more columns, each must be mentioned in the sequence you're entering values, or else have default values set. It's important to ensure that data types of the provided values match those of the specified columns. Select statement, retrieving records. The select statement is used in SQL to retrieve records from one or more tables in a database. It is the most frequently used SQL command. By specifying conditions, you can filter which records to retrieve, making it a powerful tool for data analysis. This SQL command fetches data from specified columns in a table where the specified condition is true. Column 1, column 2 represents the fields to be retrieved. Table name is where these fields reside. The where clause is optional and is used to specify the criteria that must be met for records to be selected. Where clause, filtering records. The where clause is used in SQL to filter records based on one or more conditions. It's applied to the select, update, and delete statements to specify the criteria that the rows must meet to be selected, updated, or deleted. This helps in retrieving or manipulating only those records that fulfill a specified criterion. In this example, we are selecting all columns from the employees table where the department column matches the value sales. The where clause filters out only those records from the employees table where the condition is true, ensuring that only employees working in the sales department are returned in the result set. Update statement, modifying records. The update statement in SQL is used to modify existing records in a table. This can include changing one or more columns to different values. It's crucial to specify which records to update using the where clause to prevent changing unintended records. If the where clause is omitted, all records in the table will be updated. In this example, we are increasing the salary of employees in the sales department by 5%. The update statement targets the employees table. The set clause specifies that the salary column should be updated to salary 1.05, effectively giving a 5% raise. The where clause ensures that only employees in the sales department have their salaries updated. Without this condition, all employees, regardless of department, would receive a salary increase. Delete statement, removing records. The delete statement is used in SQL to remove one or more records from a table. It is important to specify a condition using the where clause to target the specific records you want to delete. If the where clause is omitted, all records in the table will be deleted, so you must use this command with caution. This code deletes a record from the customers table where the customer ID equals 1. It targets a single record for deletion based on the specified condition. The where clause ensures that only the intended record, where customer ID is 1, is removed from the table. Order by clause, sorting records. The order by clause is used in SQL to sort the result set based on one or more columns. It can sort the data in ascending order, ASC, by default, or in descending order, DESC, when specified. Sorting allows for a more readable and organized presentation of data, especially useful when working with large datasets. In the given code snippet, we are selecting the name and age columns from the users table. The order by clause then sorts the resulting set of records based on the age column in descending order, DSC. This means the record with the highest age will be at the top of the list, and the ages decrease as you move down the list. If no ASC or DESC specifier is given, the sort defaults to ascending order. Basic aggregation functions count, sum, AVG, max, min. Aggregation functions in SQL are used to perform calculations on a set of values and return a single value. They are essential for summarizing and analyzing data stored in databases. In this example, we'll use a simple table named sales with 2 columns, product ID, integer, and amount, integer, to illustrate how each of these functions works. This SQL query demonstrates the use of 5 basic aggregation functions on the sales table. Count, product ID, returns the total number of product ID entries in the table. Sum amount calculates the total sum of values in the amount column, indicating the total sales amount. AVG amount computes the average sales amount per product. Max amount finds the highest sale amount recorded in the table, while min amount identifies the lowest sale amount. These functions help in quickly getting an overview of the data, making them fundamental for data analysis and reporting. Group by clause. The group by clause in SQL is used to arrange identical data into groups. This clause often goes with aggregate functions, count, max, min, sum, AVG, to perform an operation on each group of data. A typical use case is when you need to find the total count, average, or total of records in different categories or groups. In the provided code snippet, we're using the group by clause to count the number of employees in each department of a company. The select statement selects 2 columns, department and count employee ID. The count function computes the number of employee IDs, i.e., number of employees, in each department. Then the group by department clause groups the results by the department column, so we get a count of employees for each distinct department in the employees table. Having clause. The having clause is used in SQL to specify a search condition for a group or an aggregate. It is similar to the where clause, but the key difference is that having can filter groups of data, whereas where filters rows before grouping. Typically, the having clause is used with the group by clause, but can also be used without it if you're only filtering on aggregates. In the provided SQL query, we are selecting the department and the average salary of employees in each department from the employees table. The group by department clause groups the results by department. We are then using the having clause to filter these groups to only include those where the average salary, AVG salary, is greater than 50,000. Aliases. In SQL, aliases are used to assign a temporary name to a table or column. This can make queries easier to read and can be essential when working with complex queries and joins. Column aliases are applied in the select statement, while table aliases are generally used in the from clause. In the code example, we assign the alias name to the first name column and ID to the employee ID column using the AS keyword. When the query runs, the column headings in the result set will be name and ID instead of first name and employee ID. This doesn't change the actual column names in the database. It's just for the output of this particular query. Inner join. The inner join keyword in SQL is used to combine rows from 2 or more tables based on a related column between them. It returns rows when there is at least one match in both tables. In this query, we select the order ID from the orders table and the customer name from the customers table. The inner join combines rows from orders and customers where there is a match on the customer ID column in both tables. This results in a new table containing only the matched records, excluding any rows where there is no match. Left join. Left join, also known as left outer join, is used in SQL to combine rows from two or more tables based on a related column between them. This type of join returns all records from the left table and the matched records from the right table. If there is no match, the result is null on the side of the right table. In this code, we're selecting the order ID from the orders table and the customer name from the customers table. We're using left join to retrieve all orders, including those without a matching customer ID in customers. Orders without a matching customer will display customer name as null, ensuring we miss no orders, regardless of whether they have a linked customer or not. Right join. The right join clause in SQL is used to combine rows from two or more tables based on a related column between them, and includes all rows from the right table, even if there are no matches in the left table. This means if a row in the right table does not have a match in the left table, the result set will still include this row, but with null values in the columns of the left table. In this SQL code, we are using the right join clause to retrieve all the customers and any orders they might have. We select the order ID from the orders table and the customer name from the customers table. The right join ensures that all customers are listed, including those without any orders. If a customer doesn't have an associated order, the order ID for that row will appear as null in the result set. This query is useful for scenarios where we need to check for missing relationships, like customers who have not placed any orders. Full outer join. A full outer join in SQL combines the results of both left join and right join. It returns all rows from the left table and the right table. When there's no match, the result set will include null values on the side that lacks a match. This SQL query retrieves the name of employees and their department names from two tables, employees and departments. The full outer join ensures that all employees are listed, even those not assigned to a department, and all departments are listed, even if they have no employees. The matching condition is based on the department ID in the employees table and the ID in the departments table. If there's no corresponding department for an employee or no employee for a department, null values will appear in the output for the missing side. Union and union all. When querying databases, sometimes it's necessary to combine results from multiple select statements. SQL provides two commands to accomplish this, union and union all. The union command is used to select distinct values from two tables, whereas union all allows duplicate values. The key difference is how they handle duplicates. Let's explore both commands through an example. The first query combines names from two tables, customers and orders, removing duplicates due to union. The second query does the same, but includes duplicates with union all. This highlights union's role in ensuring distinct results versus union all's inclusivity of all results, duplicates included. Both commands require the same number and order of columns in the select statements with matching data types. Intersect. The intersect operator in SQL is used to return the intersection of two select statements, i.e., it returns only those records that are found in both select statement results. It's a handy way to find common elements between two datasets. Each select statement within the intersect must have the same number of columns with similar data types, appearing in the same order. In the provided code, column name represents the field being compared between Table 1 and Table 2. The intersect operator compares the results of the two select statements. It returns rows from column name that are present in both Table 1 and Table 2. This operation is particularly useful when you need to find records that match a certain criteria across multiple tables. It's important to note that the intersect operator automatically removes duplicates, presenting a distinct list of matching records. Except. The except keyword in SQL is used to return all rows from the first query that are not present in the second query. It works by comparing the results of two select statements and filtering out records that appear in both sets. This operation is similar to a set difference in mathematics. It's particularly useful when you need to find discrepancies between two datasets. In this code snippet, we are performing an except operation between two tables. Table 1, and Table 2, using a common column named column name. The query starts by selecting rows based on column name from Table 1. Then the except keyword is used. Following this, it selects the rows based on column name from Table 2. The final result includes all rows from the first select, Table 1, that do not have a matching entry in the second select, Table 2. It effectively filters out any rows in Table 1 that are also found in Table 2, based on the specified column. Subqueries in select, from, where clauses. A subquery in the select clause allows you to perform operations that return a single value. This is useful for returning calculated values or performing aggregates on different tables than the main query. This query retrieves the name of each customer along with the total number of orders they have. The subquery in the select clause counts the number of orders per customer by matching the customer ID in the orders table with each customer ID, C.ID, in the customers table. The result of the subquery is displayed in the order count column. Common table expressions, with clause. Common table expressions, CTE, introduced with the with clause, offer a way to write more readable and modular SQL queries. CTEs allow you to define a temporary dataset that your main query can reference. This is particularly useful for organizing complex queries, avoiding duplication of subquery code, and improving query readability. The code example uses a CTE to calculate the total sales per region from an orders table. The with clause defines a temporary result set, regional sales, that aggregates sales by region. The main query then selects regions from this CTE where their total sales exceed the average of total sales across all regions. By separating the aggregation into a CTE, the query avoids repeating the aggregation logic when calculating the average in the where clause, enhancing both readability and maintainability. Window functions. Window functions perform a calculation across a set of table rows that are somehow related to the current row. Unlike regular aggregate functions, window functions do not collapse the rows because the result is returned for every row. Commonly used for running totals, moving averages, or for ranking and partitioning data without collapsing groups. This code calculates the average salary within each department of a fictional employee's table. The select statement fetches the employee ID, department, and salary. The AVG salary over, partition by department, calculates the average salary per department, and this average is returned for each row due to the use of a window function. This means for each employee, the query also shows the average salary of their department, allowing comparisons within departments without losing individual employee details. Pattern matching with like and regular expressions. The SQL like operator is used in a where clause to search for a specified pattern in a column. There are two wildcards used in conjunction with like. Percent sign represents 0, 1, or multiple characters, and or underscore represents a single character. In this SQL query, we're selecting all columns from the employees table where the name column starts with the letter A. The percent wildcard is used to indicate that any characters may follow A, thereby matching any name that starts with A. Cast and convert functions. Cast and convert functions are used in SQL to change data types from one type to another. They are particularly useful when you need to format or manipulate data stored in a database. While cast is ANSI standard and more widely accepted across different SQL databases, convert can provide more flexibility with formatting, especially with dates and times in SQL Server. In this example, we're working with a sales table containing price and date columns. The cast function is used to change the price column data type from a numeric type to a varchar 10, making it easier to concatenate with text in SQL queries. The convert function, on the other hand, not only changes the date column data type, but also formats the date to a specific style, here, DDMMYYY, as indicated by the style number 103, making it easier to read. Both functions allow us to manipulate and present the data more effectively in the output. Case statements. The case statement in SQL is a way to introduce logic to your SQL queries, allowing for conditions to be evaluated and specific values to be returned based on those conditions. It's similar to if-else statements in programming. You could use it for a variety of tasks, such as categorizing data or applying conditional logic within your queries. The provided code demonstrates a select statement using a case structure to classify individuals from the people table into different age groups. For each person, it selects their name and age. It then evaluates the person's age. If the age is less than 18, the person is classified as a minor. If the age is between 18 and 64 inclusive, the person is classified as an adult. Otherwise, for ages 65 and above, the classification is senior. The result of the case statement is displayed in a new column named Age Group. This showcases how case statements can be utilized to dynamically assign values in a result set based on specific conditions. Introduction to database design. Database design is a crucial step in database development that aims to organize data in a way that reduces redundancy and dependency while ensuring data integrity and storage efficiency. The process involves understanding the data needs, defining the database structure, and applying normalization principles to ensure the database's scalability and performance. This SQL code snippet illustrates the creation of a simple table named Students. The table is designed to store student information, including a unique student ID, acting as the primary key, first and last names, email addresses, and majors. This example highlights the importance of defining appropriate data types, such as int and varchar, and the necessity of identifying a primary key to ensure unique identification of each record. Understanding normalization. Normalization in databases is a process aimed at organizing the attributes and tables of a database to reduce data redundancy and improve data integrity. The primary objective is to divide large tables into smaller, manageable tables and link them using relationships. The process involves applying a series of rules, or normal forms, to ensure the database is structured correctly. In this SQL query, we're illustrating a simple form of normalizing data by separating employee information and department information into two tables and linking them with a foreign key, dept ID. Employees contain all employee-specific information, and departments house department-specific details. The join operation demonstrates how normalization allows us to efficiently query related data from separate tables, improving readability and maintaining data integrity by avoiding duplication. First normal form, 1NF. The first normal form, 1NF, is a fundamental concept in database normalization that aims to minimize redundancy within a database. Achieving 1NF involves organizing data into tables such that each column contains atomic or indivisible values, and each row represents a unique record with no repeating groups or arrays. This ensures data integrity and simplifies the database structure. In the given SQL code, we create a students table that illustrates the 1NF concept. Each attribute, student ID, full name, phone number, subject, is atomic, meaning they hold single, indivisible values. There are no columns designed to store lists or arrays, ensuring that each column holds one value per row. Moreover, student ID is defined as the primary key, enforcing uniqueness across rows. This table structure adheres to the 1NF rules by avoiding duplicate records and eliminating the possibility of multi-valued attributes. Second normal form, 2NF. The second normal form, 2NF, is a step in the database normalization process that reduces redundancy and dependency by ensuring that all non-key attributes are fully functional dependent on the primary key. This means that each non-key attribute must depend on the whole primary key, not just part of it, which is especially relevant in tables with composite primary keys, i.e., primary keys consisting of more than one column. Let's consider an example table that is not in 2NF and how to normalize it into 2NF. The original table sales is not in 2NF because the region ID attribute is only partially dependent on the primary key, salesperson ID, product ID, violating 2NF's rule of full functional dependency. To normalize it into 2NF, we remove the partially dependent attribute, region ID, and create a new table, sales regions, that associates salespersons with regions. This design ensures that all non-key attributes in the sales table are fully functionally dependent on its composite primary key, adhering to the 2NF rules. Additionally, by separating regions into a different table, we reduce redundancy and make the database structure more flexible for future amendments. Third normal form, 3NF. In the process of database normalization, third normal form, 3NF, is crucial for eliminating redundant data and ensuring data integrity. A table is considered to be in 3NF if it is in second normal form, 2NF, and all of its attributes are not only functionally dependent on the primary key, but also directly dependent. This means there should be no transitive dependency for non-prime attributes to ensure that data is stored in a practically efficient manner. The provided SQL creates a table named employees, aiming for 3NF by ensuring each non-key attribute, employee name, department ID, department name, is directly dependent on the primary key, employee ID. However, department name is transitively dependent on employee ID through department ID, violating 3NF. Correctly implementing 3NF, department name should be moved to a separate departments table where it is directly dependent on department ID, the primary key of departments table, thus eliminating transitive dependency and ensuring the design meets 3NF criteria. Boyce Codd Normal Form, BCNF. Boyce Codd Normal Form BCNF is a stricter version of the third normal form 3NF, aimed at resolving anomalies in database design. BCNF is reached when every determinant in a table is a candidate key. In the provided SQL code, we create a table named Student Courses that potentially violates BCNF, because while Student ID Course ID is the primary key, and thus a candidate key making it compliant with BCNF, if Instructor ID determines Course ID, or vice versa, without being a candidate key, this design would violate BCNF. Each non-primary key must not be a determinant in a BCNF-compliant table unless it is a part of a candidate key. To resolve, we may need to decompose this table further. Denormalization techniques. Denormalization is the process of intentionally adding redundancy to a normalized database to improve its performance. This involves altering table structures to combine data, which can reduce the number of joins and improve query speed. It's a strategy used carefully to optimize read operations at the cost of making write operations potentially more complex or slower. In this example, we've added a customer name column to the orders table and populated it with the customer's name from the customers table. Instead of joining the orders table with the customers table every time we need the customer's name, we store it directly in the orders table. This technique reduces the need for complex joins, thereby potentially improving query performance. However, it introduces redundancy and can lead to data anomalies if not carefully managed, especially during insert, update, or delete operations. Understanding indexes. Indexes are tools that help speed up query performance in databases. Think of an index in a book, which helps you to quickly find the information you're looking for without reading every page. Similar concept applies in databases, allowing faster data retrieval. This SQL statement creates an index named IDEs name on the column name of table name. When a query searches data related to column name, it can use IDEs name to find results faster. However, indexes do increase storage usage and can slow down data insertions and updates, as the index itself must be updated. Creating indexes. Indexes are special lookup tables that the database search engine can use to speed up data retrieval. Simply put, an index is a pointer to data in a table. Creating an index involves the SQL command createIndex. It's crucial to choose the columns wisely for indexing, since the wrong choice can degrade performance, especially during data modifications, insert, update, delete. This SQL statement creates an index named IDEs customer name on the customers table, specifically on the customer name column. The database engine can now use this index to quickly find data by customer name, significantly speeding up queries that involve searching or sorting by this column. It's important to note that while indexes improve query performance, they can take up additional storage space and may slow down data modification operations. Using indexes to improve query performance. Indexes in SQL are used to speed up the retrieval of data from a database table. They work similarly to an index in a book, allowing the database engine to quickly locate the data without scanning the entire table. Creating an index on columns that are often used in where clauses, join conditions, or as part of an order by can significantly improve query performance. This code snippet demonstrates how to create an index named IDEs customer name on the name column of the customers table. By executing this statement, the database creates an index that can be used to quickly find customer names. When a query searches for a specific name, the database uses the index to locate the names much faster than scanning the whole table. This is particularly useful for large tables and can dramatically reduce query execution time. Index types: unique, composite, full text. A unique index ensures that all the values in a column or a group of columns are distinct from each other. It is crucial for maintaining data integrity by preventing duplicate entries in the table. The code snippet creates a unique index named IDEs unique column on the column name of table name. This index enforces uniqueness, meaning no two rows can have the same value in column name. It's instrumental for columns like email addresses or user IDs, where each value must be unique. Viewing execution plans. Understanding how SQL queries are executed can help in optimizing performance. Execution plans provide insights into the steps and resources involved in executing a SQL command. Here, we'll see how to view execution plans using SQL Server Management Studio, SSMS. The provided SQL commands enable the display of the execution plan for a query without actually running the query. Set Show Plan Text On instructs SQL Server to return the execution plan as text. After executing this, any subsequent query you run will return its execution plan instead of the actual results. For the execution plan of a specific query, you place your query right after the Set Show Plan Text On. To return to normal query execution and get actual results from queries, you must disable this feature by running Set Show Plan Text Off. Optimizing queries. Optimizing queries is essential for improving the performance and efficiency of your database operations. It involves analyzing queries to reduce execution time and resource consumption. A common method is to use indexes strategically. The initial select query retrieves all customers over 30 years old living in New York. Without indexes, the database scans the entire table, which is inefficient for large datasets. By creating two indexes on the age and city columns, using the create index statements, the database can quickly locate the relevant rows. The first index aids in rapidly identifying customers by age, and the second index further narrows down the result set to those living in New York. This optimized approach significantly reduces the query execution time by avoiding full table scans and directly accessing the needed data. Database Engine Tuning Advisor. The Database Engine Tuning Advisor, DTA, is a tool provided by SQL Server to help users optimize the performance of their databases. It analyzes database workloads and recommends solutions to improve efficiency. Here, we simulate how to run a simple query analysis with DTA via T-SQL to understand its basic application. In this T-SQL script, AdventureWorks 2012 database is selected for analysis. The SPMS for each table stored procedure iterates through each table in the database, executing a command for each. The command used here is a print statement, followed by the dbcc show statistics command for the primary key of each table, which shows the distribution of key values and provides the statistics object and histogram used by the query optimizer to choose indexes during query execution. This example script mimics how detailed data about index usage and performance could be extracted for analysis, similar to beginning steps one might perform before using more advanced features of the Database Engine Tuning Advisor for comprehensive tuning advisors. ACID properties. ACID properties ensure that database transactions are processed reliably and help maintain the integrity of a database by following four key principles: atomicity, consistency, isolation, and durability. Understanding these concepts is crucial for implementing robust database systems that can handle concurrent user requests and potential system failures without losing or corrupting data. In this example, two accounts are involved in a transaction with money being transferred from one to the other. Atomicity ensures that both updates are completed successfully or none at all, preventing an uneven deduction or addition. Consistency ensures that the transaction leaves the system in a consistent state, adhering to all database rules, like not allowing balance to go negative. Isolation ensures that other operations cannot interfere with this transaction. And durability ensures that once the transaction is committed, it will not be lost even in the case of a system failure. Begin transaction, commit, and rollback. In SQL, transactions are used to ensure data integrity and to handle database errors. A transaction is a sequence of one or more SQL statements that are executed as a single unit. The begin transaction command marks the starting point of an explicit transaction. Commit is used to save all the changes made by the transaction to the database. Rollback is used to undo the changes made by the transaction if an error occurs. The code snippet starts a transaction, adds a new employee, Jane Doe, to the employees table, and commits the transaction, which means the changes are saved to the database. If the transaction were to fail, typically due to an SQL statement error or a system failure before the commit, none of the changes would be saved. The second part shows starting another transaction to add John Doe to the employees table, but it explicitly demonstrates a rollback, which undoes the insert operation. In reality, the rollback would be conditional, based on error detection in application logic. Save points. In the context of database transactions, a save point is a way to partially roll back the effects of a transaction without aborting the entire transaction. This is useful when you want to save a checkpoint during a long transaction, allowing you to undo some changes without losing all of the work done up until that point. This can be particularly useful in complex operations where certain steps might fail and you do not want to restart the transaction from the beginning. In this code snippet, we start a transaction with begin. After performing some operations, we mark a save point named mySavePoint. This acts like a checkpoint within our transaction. Then, we perform more operations. If we decide that the recent operations need to be undone, we can roll back to mySavePoint using rollback to SavePoint mySavePoint. This undoes the operations performed after the save point was set, but keeps the changes made before the save point. Finally, we continue with more operations and commit the transaction with commit. Note that committing the transaction finalizes all changes made since begin, including those done after rolling back to a save point. Locks, shared and exclusive locks. Locks in SQL are mechanisms to manage concurrency, ensuring data integrity and consistency during transactions. Shared locks allow multiple transactions to read a resource but not modify it, promoting concurrency. Exclusive locks restrict access to a resource for reading or writing exclusively to one transaction, prohibit others' access. In this example, we initiate a transaction and select rows from the accounts table with a hold lock, which is an exclusive lock that prevents other transactions from reading or modifying the selected rows until the current transaction is committed or rolled back. The update statement then modifies the balance of account 1. Finally, the transaction is committed, releasing the lock and making the updates visible to other transactions. This pattern helps in situations where we need to ensure that the selected data remains stable through the duration of our transaction. Isolation levels. Isolation levels in SQL databases define the degree to which the transactions are isolated from each other, affecting the visibility of changes made by concurrent transactions. They help balance between performance and accuracy, preventing issues such as dirty reads, non-repeatable reads, and phantom reads. The 4 standard levels are read uncommitted, read committed, repeatable read, and serializable. The code set transaction isolation level read committed is used to set the isolation level of transactions in a database session to read committed. At this level, a transaction cannot see uncommitted changes made by other transactions, which prevents dirty reads. However, it's still possible for non-repeatable reads or phantom reads to occur, as the data read by a transaction can change if other transactions commit changes to the same data. Deadlocks and how to avoid them. A deadlock occurs in a database system when 2 or more transactions are waiting indefinitely for one another to release locks. It's a common issue in concurrent systems where different transactions lock resources that the other transactions need. Deadlocks can be avoided through various strategies, one being the use of timeout or lock timeout. In this example, the set lock timeout 5000 command instructs SQL Server to wait for a maximum of 5000 milliseconds or 5 seconds for a lock to be released. If the lock isn't released within this time frame, the SQL operation will be terminated and the transaction rolled back, hence preventing a deadlock situation. It's a proactive approach that allows a DBMS to avoid getting stuck in a deadlock by aborting operations that cannot be completed within a reasonable timeframe. This helps in maintaining system responsiveness and preventing transactional gridlock. Creating and using stored procedures. A stored procedure is a prepared SQL code that you can save and reuse over again. It's used to execute the same set of operations multiple times, which can help improve your database performance. Here, we'll create a simple stored procedure to select all records from a customer's table. The create procedure getAllCustomers command annotates the creation of a stored procedure named getAllCustomers. The as keyword follows, indicating the start of the procedure's definition. Between the begin and end keywords is the SQL statement the procedure will execute, in this case, selecting all records from the customer's table. To use this stored procedure, you would execute a call such as exec getAllCustomers, which runs the code encapsulated by the stored procedure, eliminating the need to manually type the select query each time. Input and output parameters. Stored procedures in SQL can accept input parameters, which allow you to pass data into the procedure, and output parameters, which enable you to return data from the procedure. This feature makes stored procedures flexible and powerful for various database operations. In the example, getEmployeeInfo is a stored procedure designed to get an employee's name by their ID. The @EmployeeID is an input parameter where you pass the employee's ID you're querying. The @EmployeeName is an output parameter, which will store and return the employee's name after executing the procedure. Inside the procedure, a simple select statement assigns the employee's name to the @EmployeeName output parameter using the employee ID provided. Variable declaration and conditional statements within stored procedures. Stored procedures in SQL allow you to execute complex operations on a database. A crucial part of creating stored procedures involves declaring variables to store data temporarily and implementing logic through conditional statements to direct the flow of execution based on certain conditions. Let's explore how to declare variables and use simple conditional statements in the context of stored procedures. In this SQL code snippet, we begin by creating a stored procedure named example procedure. Inside it, we declare an integer variable @EmployeeAge and assign it the value 25. The conditional statement, ifs, checks if @EmployeeAge is greater than 18. If the condition is true, it prints employee is an adult. Otherwise, it prints employee is a minor. This illustrates how to declare variables and use basic conditional logic within a stored procedure to control the flow of execution based on specific conditions. Creating and managing triggers. Triggers are special types of stored procedures that automatically execute or fire when a specified event occurs in the database, such as insert, update, or delete operations on a table. They're used for maintaining data integrity, enforcing business rules, and auditing changes. Let's see how to create a simple trigger that automatically updates the last modified timestamp of a record in a table whenever that record is updated. This code snippet demonstrates the creation of a trigger named TUG_update_timestamp on a table named yourTableName. The trigger is set to fire after an update operation occurs on the table. The AS keyword begins the body of the trigger, where the actual logic is specified. Inside, the trigger performs an update operation on the yourTableName, setting the last modified column to the current timestamp, indicating when the update occurred. The from inserted clause uses a special table called inserted, which SQL Server creates internally to hold the new values during an update or insert operation. The where clause ensures that only the rows that were updated have their last modified timestamp updated by matching the primary key of the table, yourTableName, with that of the inserted table. Instead of and after triggers. Instead of triggers are used mainly on views that do not support direct updates or inserts. And instead of trigger steps in to perform specified actions in place of the attempted operation. In this code, an instead of trigger named instead of insert is created on a view called viewName. Instead of inserting data directly into the view, this trigger intercepts the insert operation and inserts the data into table name. Using the values provided in the inserted pseudotable, which SQL Server automatically populates with the row that was attempted to be inserted into the view. Cursors. In SQL, a cursor is a tool that allows you to iterate over the rows of a result set one row at a time. This can be particularly useful when you need to process data row by row, which might not be as straightforward with set-based SQL operations. Cursors are often used within stored procedures or triggers when specific row-level operations are required. This code snippet demonstrates the basic structure for defining, opening, and navigating through a SQL cursor. The declare statement initializes the cursor with a select query. The open statement prepares the cursor for fetching rows. Fetch next retrieves the next row and stores it into a variable. The loop continues as long as @fetchStatus returns 0, indicating there are more rows. Within the loop, row-specific operations can be performed. Finally, the cursor is closed and deallocated to free resources. Overview of SSRS. SQL Server Reporting Services, SSRS, is a server-based report-generating software system from Microsoft. It is used to produce formatted reports, which include tables in the form of data, graph, and free-form reports from relational or multi-dimensional data sources. Reports can be published and accessed on a server-based network. The code snippet represents a simple SQL query that could be used in an SSRS report to fetch the names, departments, and salaries of employees who work in the sales department. This example shows how data can be retrieved from a database, which is the first step in creating a report in SSRS. The result of such a query can be used to populate a table in an SSRS report, showcasing how SSRS serves as a bridge between raw data and a formatted report, suitable for business decision-making. Creating basic reports. Creating a basic report in SSRS involves constructing a simple query that retrieves the data you want to display, and then using the report wizard in SQL Server Data Tools, SSDT, to generate the report. Let's walk through creating a basic report that displays a list of products from a sample database. This SQL statement selects the product ID, product name, and price columns from the products table, ordering the results alphabetically by product name. In SSRS, this query would serve as the dataset for our report. The next steps in report creation, using this dataset, involve designing the report layout in the Report Designer in SSDT, where fields from this query can be dragged onto the report template. This process, while not captured in a single code block, illustrates the foundational step of report creation by defining what data the report will display. Report parameters and expressions. Report parameters in SSRS allow you to create dynamic reports where users can specify their criteria, and expressions enable you to customize the content or appearance based on conditions or calculations. By combining these features, reports become more flexible and powerful. This expression checks if the sales field value is greater than 10,000. If true, it displays high, otherwise it shows normal. This is often used in a text box property within the report to dynamically show data status. Expressions like this help in making reports interactive and user-responsive by changing content or format based on the data. Deploying and managing reports. Deploying reports in SSRS involves transferring reports from the development environment to the report server where end users can access them. Managing reports includes setting up subscriptions, assigning permissions, and monitoring report usage. We'll focus on deploying a report using the report server web service. This script uses the rs.exe utility, a command line tool that comes with SSRS, to deploy a report. The mash-i parameter specifies the script file to run, here deploy report.rss, which contains the deployment logic. The mash-s parameter is for the report server's URL. Parameters like report path and report name are passed using -v, determining where and under what name the report should be deployed. Lastly, NAS-U and NAS-P are used to provide your credentials to authenticate against the report server. Overview of SIS. SQL Server Integration Services, SSIS, is a component of the Microsoft SQL Server database software that can be used to perform a broad range of data migration tasks. SSIS is a platform for data integration and workflow applications. It features a fast and flexible data warehousing tool used for data extraction, transformation, and loading (ETL). The tool may also be used to automate maintenance of SQL Server databases and updates to multidimensional cube data. SSIS enables users to integrate and transform data from various sources into a unified format. It allows the creation of workflows, which can automate tasks such as copying or downloading files, which would then be inserted into a database. Data transformations can include aggregating, merging, and cleansing data before it's loaded into a destination, ensuring data integrity and usability. SSIS packages, the unit of work in SSIS, can be created using a visual interface in SQL Server Data Tools, SSDT, enabling users to build complex data integration workflows with minimal coding. Creating SSIS packages. SSIS packages are a vital part of SQL Server integration services, allowing you to integrate and transform data between different sources. Here, we'll showcase the creation of a basic SIS package that extracts data from a SQL Server database, transforms it, and then loads it into another database. Creating an SSIS package starts with launching SQL Server Data Tools, SSDT, and creating a new integration services project. Within this project, you define data flow tasks. Each data flow task consists of components that specify the source of the data, e.g. a SQL Server table, any data transformations, like converting data types or merging data from different sources, and the destination, where the data should be loaded, such as a different database or a flat file. The visual design nature of SSDT allows for a clear and simplified construction of potentially complex data integration tasks. No direct code is provided here, as the creation process is GUI-driven in SSDT. SSIS package management and deployment. To deploy SSIS packages, SQL Server provides a deployment wizard that simplifies the process. This approach helps in moving packages from a development environment to a production environment efficiently. The steps provided are a guide on deploying SSIS packages using the deployment wizard. After opening the SQL Server Data Tools, SSDT, deploying begins by right-clicking the project and selecting Deploy. The deployment wizard then guides through selecting the destination server or SQL Server instance and deploying the packages. This method ensures that the packages are transferred correctly and are ready to execute in the new environment. Introduction to NoSQL databases. NoSQL databases provide a mechanism for storage and retrieval of data that is modeled in other than the tabular relations used in relational databases. Such databases have become highly popular for their scalability, performance, and flexible schema designs. Unlike SQL databases that use structured query language, SQL, for defining and manipulating data, NoSQL databases can store large volumes of structured, semi-structured, or unstructured data with quick access. The provided code snippet demonstrates how to insert a document into a NoSQL database collection using MongoDB, a popular NoSQL database. Here, a new document representing a product, in this case a laptop, with various attributes such as name, price, and a nested object for specifications, is added to the products collection. This operation is different from SQL databases where you would need to define a schema beforehand. In NoSQL, the document structure can vary from one document to another within the same collection, highlighting the schema flexibility of NoSQL databases. Types of NoSQL databases: document, key value, wide column, graph. NoSQL databases are designed to handle a wide variety of data models, including document, key value, wide column, and graph formats. Each type offers unique advantages depending on the specific requirements of the application. Document databases store data as documents, typically in JSON or BSON formats, making them ideal for storing and querying nested data. Key value databases store data as a collection of key value pairs, optimized for quick retrieval based on a specific key. Wide column stores utilize tables, rows, and dynamic columns to efficiently query large datasets. Graph databases are designed to store and navigate relationships between data points efficiently, using nodes, edges, and properties. Overview of NewSQL. NewSQL is a class of modern relational database management systems that seeks to provide the scalability of NoSQL systems for online transaction processing (OLTP) workloads while maintaining the ACID guarantees of a traditional database system. This approach often involves innovative architecture designs that depart from the classical RDBMS structure without giving up the SQL language and its ecosystem. Let's look at an example scenario where we might inquire about the status of a NewSQL database. This SQL code snippet is requesting the current status of a server with an ID of 1 from a NewSQL database system. It uses a select statement, which is a standard SQL operation used to query data from databases. The request is made against a hypothetical table named System Health, which might store information about the health and status of different parts of the NewSQL system. This example illustrates the use of familiar SQL syntax to interact with NewSQL databases, reflecting their goal to combine the advantages of SQL and NoSQL databases. Difference between SQL, NoSQL, and NewSQL. Understanding the landscape of database technologies is crucial for both database administrators and developers. SQL, NoSQL, and NewSQL represent three different approaches to data storage and management. SQL, structured query language. Databases are relational, offering complex queries and transactions. NoSQL databases are non-relational, designed for specific data models and have flexible schemas. NewSQL combines the scalability of NoSQL with the transactional guarantees of SQL databases. The code snippets provided illustrate basic queries across the three database paradigms. The first line queries a SQL database, fetching records from the orders table, where the order date is on or after January 1st, 2021. The second line is a query for a NoSQL database, specifically MongoDB, demonstrating a document-based query for records with an order date on or after January 1st, 2021. The third line mimics the first, intending to showcase that NewSQL databases allow for a similar SQL-like syntax, combining traditional SQL capabilities with modern scalability and performance enhancements. Use cases for NoSQL and NewSQL. NoSQL databases are designed to handle a wide variety of data models, including document, graph, key value, and columnar. They are particularly well suited for applications requiring large amounts of non-relational data, horizontal scalability, and flexibility in terms of data schema. Below is a conceptual representation of how a document-oriented NoSQL database might store data. This code snippet illustrates a JSON document that could be stored in a NoSQL database like MongoDB. In this representation, a single document can contain nested fields such as orders and items, showcasing the database's ability to handle complex, hierarchical data structures. This flexibility, combined with the ability to scale horizontally, spread out over many servers, makes NoSQL databases ideal for applications like content management, big data, and real-time analytics, where the data model may not fit well into a rigid, tabular schema. Data warehousing. Data warehousing involves consolidating data from different sources into a single, comprehensive database designed for analysis and reporting, rather than transaction processing. It allows organizations to make more informed decisions by analyzing historical data. Let's look at a basic SQL query used to extract and summarize sales data from a data warehouse. This SQL query retrieves the sum of sales grouped by region from a sales data table, then orders the results by total sales in descending order. Such queries are common in data warehousing to perform aggregations and obtain insights into the business performance across different dimensions, like geographic regions in this example. Big data and SQL. As data volumes grow exponentially, traditional relational databases struggle to cope with big data. Big data refers to extremely large datasets that may be analyzed computationally to reveal patterns, trends, and associations. SQL, while traditionally associated with relational databases, also plays a vital role in big data analytics. Tools like Apache Hive and Spark SQL allow SQL to be used to query and manage big data stored in distributed systems like HDFS, Hadoop Distributed File System. In the context of big data, the above SQL query could be executed over a distributed SQL query engine like Hive or Spark SQL. To aggregate transaction data, it counts the total transactions and sums up the amount for transactions since the beginning of 2023. Despite the simplicity of SQL, it's powerful enough to handle vast amounts of data through systems designed to process big data, demonstrating SQL's versatility in both traditional and modern data environments. SQL in cloud environments, AWS RDS, Azure SQL Database. Cloud environments like AWS RDS and Azure SQL Database make SQL databases more accessible while providing scalability, availability, and security. Here's a basic example of creating a database in AWS RDS. This SQL command creates a new database named My Database. In a cloud environment, such as AWS RDS, you'd first set up an RDS instance through the AWS Management Console or CLI. After configuring your RDS instance, e.g., choosing an engine like MySQL, PostgreSQL, you connect to your instance using a SQL client. Then, execute this command to initialize your database. Depending on your selected engine, the exact syntax may vary slightly. SQL Security Best Practices. Securing SQL databases is crucial to protect sensitive data from unauthorized access and SQL injection attacks. Implementing best practices enhances data integrity and confidentiality. One key practice is to use parameterized queries to prevent SQL injection. The code demonstrates a parameterized query where DAT placeholders are used for input values, instead of directly including user inputs in the SQL statement. This approach prevents attackers from injecting malicious SQL code. By using placeholders, the database engine treats user inputs as data, not executable code, significantly reducing the risk of SQL injection attacks. SQL and machine learning integration. Integrating machine learning (ML) with SQL databases opens up data in SQL databases for predictive analytics without the need to export data to a different environment. This scenario typically uses a SQL extension or a stored procedure that calls an ML model. Here's a basic example using SQL Server's p-execute external script to call a Python machine learning model. This code block demonstrates how to execute a Python script from within SQL Server using the stored procedure s-execute external script. The procedure specifies the language of the script, Python, the script content where a machine learning model is applied to the input data, with the assumption that the model is already loaded, and the source of the input data is a SQL table, your data table. The Python script takes the input data, applies a predictive model, and returns the result, which can be processed or stored in SQL Server. This allows for leveraging machine learning directly within your database, enabling efficient data processing and reducing the need for data movement. Emerging trends in SQL and database technologies. NewSQL databases are an emerging category designed to combine the scalability of NoSQL systems with the ACID guarantees of traditional SQL databases. They are optimized for online transaction processing, OLTP, and support SQL querying language, making them suitable for applications requiring fast, reliable transactions. In this SQL query, we are selecting all columns from a hypothetical table called NewSQL table, where the transaction speed column value is fast. This demonstrates a basic SQL operation in a NewSQL database environment, highlighting its capability to handle operations similar to those in traditional SQL databases, but with enhanced performance and scalability features.